Hello students. So in this class I will start with a new concept. So that is radiation resistance of a short electric dipole. So let us now calculate the radiation resistance of short dipole. So this may be done as follows using Poynting vector concept. So Poynting vector of an far field is integrated over a large sphere to obtain the total power radiated. So this is the power is then equated to I square R, where I is the RMS current on the dipole and R is the resistance. Is called a radiation resistance of a dipole. The average Poynting vector is given as S is equal to half real part of E cross H star, right? The far field components of E theta and H phi, so that the radial component of Poynting vector is SR is equal to half a real part of E theta H phi star, where E theta and H phi star are complex. Now see here, this diagram suggests that within the radiant sphere at r equal to lambda by 2 pi, that is 0.16 lambda, the situation is like that inside a resonator with a high density pulsating energy accompanying by leakage which is radiated. You can see here, so there is a dipole around which there is a n circle. It's a radiant sphere resonator, right? So radiations are in all directions. So you can observe here. So now let us calculate the radiation resistance of such a short dipole. So within that range, that is 0.16 lambda sphere, right? The far field components are related by intrinsic impedance of the medium. Hence E theta, which is equal to H phi Z, which is equal to phi under root mu by epsilon, right? So SR is equal to half real part Z H phi and H phi star, right? So 1 by 2 H phi magnitude square real part of Z. So you can rewrite this one as half H phi square, its magnitude under root mu by epsilon. The power, total power P radiated is given as P is equal to double integral SR ds, where ds is the differential surface. So which is equal to half under root mu by epsilon. So 0 to 2 pi, 0 to 2 pi H phi square R square sin theta d theta d phi, where the angles are as shown in diagram is the absolute value epsilon. H phi is the absolute value of magnetic field, which is given as H phi is equal to omega I naught L sin theta whole divided by 4 pi CR. So you can substitute this H phi in the above equation, that is P is given as 1 by 32 under root mu by epsilon beta square I naught square L square whole divided by pi square. So integral 0 to 2 pi, 0 to pi sin cube theta sin theta d phi. Alright, so you can solve this double integral. So by making or splitting into two terms, 0 to 2 pi with a d phi, that is a 2 pi answer, 0 to pi sin cube theta d theta. So you can rewrite this integral, say 0 to pi by 2 times sin cube theta d theta by using the standard formula. So you can get the double integral. So that is 2 times of 0 to pi by 2 sin cube theta d theta. So by using the reduction formula, so we can write 8 pi by 3. So therefore above equation can be rewritten as P is equal to under root mu by epsilon, so beta square I naught square L square by 2 pi. This is the average power or rate at which energy is streaming out of a sphere surrounding the dipole. Hence it is equal to the power radiated. Assuming no loss, it is also equal to the power delivered to the dipole. Therefore P must be equal to the square of RMS current flowing on dipole, as a resistance RR is called the radiation resistance of a dipole. Therefore mu by under root mu by epsilon beta square I naught square L square whole divided by 12 pi, which is equal to I naught by under root whole square RR, right? solving for RR, that is a radiation resistance, RR is equal to under root mu by epsilon beta square L square by 6 pi. For air or vacuum, mu by epsilon is what, 377 or 120 pi, right? So therefore dipole with a uniform current, its radiation resistance is given as RR is equal to 80 pi square L by lambda whole square, which is equal to 80 pi square L lambda square, which is equal to 790 L lambda square ohms, right? So this is what the required expression for what, radiation resistance of a short dipole antenna, which is 790 L lambda square. This is what the required expression. So in the next topic, so we'll continue with that. It's a radiation resistance of a lambda by 2 antenna. To find the radiation resistance, a Poynting vector is integrated over large sphere yielding the power radiated, and this power is then equated to I naught by root divided by root 2 whole square to R naught, where R naught is the radiation resistance at a current maximum point, and the I naught is the peak value and the time of current at this point, right? The total power radiated equation can be given, and in terms of H phi for a short dipole, where H phi is the absolute value, hence the corresponding value of H phi for a linear antenna is obtained by substituting a magnitude of J I naught is equal to I naught, right? So we can rewrite that equation as P is equal to 15 I naught square by pi whole divided by 0 to 2 pi integral, so 0 to pi cos beta L by 2 cos theta minus cos beta L by 2 whole bracket square whole divided by sin theta d theta d phi. So need to integrate this one, since there is a one term which are involved in a d phi with the integral 0 to 2 pi, so that results in 2 pi. So only the terms are left out with the theta angles, right? So you can rewrite this integral as 30 I naught square integral 0 to pi cos beta L by 2 cos theta minus cos beta L by 2 sin theta d theta. So equating the radiated power is given as I naught square R naught by 2. So therefore we have P is equal to I naught square R naught by 2. Why? Because if you square this term, so I naught square will become, right, under root 2 square will be what, 2, so R naught will be as it is. Substituting this P quantity, that is P is equal to I naught square R naught by 2, so in the above equation, so therefore R naught is equal to 60 and integral of 0 to pi cos beta L by 2 cos theta minus cos beta L by 2 whole divided by sin theta whole square d theta, where the radiation resistance R naught is referred to be the current maximum. So in the case of lambda by 2 antenna, this is at the center of antenna or at the terminals of transmission line, right? So proceeding with the evaluation of the previous equation, that is integral psi. So in the cosine integral sine, so it may be shown that a radiation resistance of an lambda by 2 antenna is R equal to 30 Cn 2 pi, which is equal to 30 into 2.44. This is equal to 73 ohm. This is a well-known value for radiation resistance of for a thin linear center-fed lambda by 2 antenna with sinusoidal current distribution. The terminal impedance also includes some inductive reactance as discussed the previous, right? Therefore Z is equal to 73 plus J 42 plus 0.5 ohms, right? To make reactance 0, so that is to make the antenna resonant requires that antenna is shorted for few percent less than lambda by 2. This is shortening also results in a reduction in the value of radiation resistance to the about 65 ohm. Therefore, radiation resistance of lambda by 2 antenna is what? 73 ohm, right?